hardly need to emphasize this point at CITA, that the great thing about doing cosmology these days, as opposed to when I was a grad student long ago, is that there's all this data, and you have to respect the data. It's really different time. So let me introduce you to one piece of data that has influenced this work. How many people know the story behind this photo? This is the Hubble servicing mission. This is the HST. And the basketball was used by Hubble to win the championship. When he was captain of the University of Chicago basketball team long ago. And this slide will stay long enough that you can figure out it's not actually the same ball, but it's part of the same story. And so I'm not going to, and this sort of ball went up on a servicing mission. And it's a really nice story. Rocky Call was a good resource for learning more about the story. I'm not going to tell more about it during my talk, except to say that Rocky told me the story. Then I really liked it, so he sent me a picture. And I sent back saying, well, I love the picture, I love the story, but I'm a little unhappy because it's clearly evidence against inflation. And of course, you don't mess with Rocky, right? So he bounced right back. It's just evidence against eternal inflation. So now that we have data against eternal inflation, I've had to take that more seriously. But on a more serious note, another influence on this talk, this actually started long ago. So inflation, I'll be introducing the necessary ingredients and all that. But inflation is a theory about the start of the universe. And there is a question of how inflation started, and how do you think about the initial conditions of the universe anyway? And there, even in decades ago, people were wondering about that, and there was lots of debate, lots of people had their favorite wave functions of the universe, and they would push back and forth about their favorite ideas and post insulting cartoons on their slides about each other. And there was a very passionate debate about whose theory of the wave function of the universe is right. Oh, this is great. I'm glad to know that Google wants to synchronize my calendar, even though I try to carefully turn the internet on. And so I found that debate. So there's lots of, did you like the Hawking instanton, the Linde instanton, or whatever. I always found that debate very unconvincing, uncompelling, and wanted to think of a better way to think about the conditions of the universe. And I realized early on that if we could think of the universe fundamentally in an equilibrium state, in cosmology, there's fluctuations out of equilibrium, then we would have a very different perspective on initial conditions. Namely, we wouldn't really have it. A system internal in equilibrium does not, there's no meaning to initial conditions. It's all swallowed up in the equilibration, and it cycles through its fluctuations without needing any separate theory of initial conditions. The state of a system, the probability of finding a system in a certain state is given by a Boltzmann factor, which is just related to the Hamiltonian, the energy, the laws of physics of the system. So if you know the laws of physics, you know the probability to assign to a given state. And so I realized from early on that that, to me, is a much deeper way about thinking of the state of the universe, because it completely eliminated all these weird arguments about whose wave function of the universe was better. Because it was really hard for me to imagine the universe would be listening to these debates. So I found that very attractive. The only trouble was, back in the 80s, when I was first starting to think about this, there was no clear way how you could think of the universe. Physically, how you would make sense of an idea that the universe could be in an equilibrium state. And so that's changed with the discovery of the cosmic acceleration. So what I'm going to do is just leave that thought for a moment and come back to it later talk. We're going to come back to the idea of the universe in an equilibrium state was influenced by the cosmological constant. Now I want to pick up another thread, which is that cosmic inflation has done fantastically well as a phenomenology of what happened just before the regular Big Bang. It's done fantastically well, but inflation, if you read the early papers, we were especially excited of inflation being, about the idea that inflation would be an explanation for why it is natural to find the universe in the state we find it today, why it's likely to, the universe is likely to form we find. And that goal, that initial goal, the thing that got us most excited in the early days, has actually proven very difficult to realize. And that's the topic of this talk, is struggling to realize that goal. I think as the talk progresses, I urge you all to take a skeptical point of view on this, because another point of view you can take is, oh, okay, so those poor guys 30 years ago hoped to do something wonderful and explain everything about the universe. But in the meantime, they found something for us to calculate. So when we take beautiful data on the CMB or whatever, we have curves to fit and a phenomenology to interpret the data. And maybe that's a really great deal. And maybe, as you'll see, I'll be developing sort of the problems we've encountered with this grand goal. Maybe we should count ourselves lucky that we have this and not worry too much about the grand goal. So I want to plant that skeptical thought in your mind. Although clearly I think it's worthwhile spending some of my time exploring this. And that's what the topic of today's talk is. But I instruct you to be skeptical and keep this thought in mind. So I think it's good. I think it's healthy to ask that question as we go. So in this talk, I have a very introductory thing that will be familiar to most of you. It will get us all on the same page, get you used to the kind of pictures I'm going to use to illustrate things. I'm going to discuss eternal inflation, which is sort of the most popular idea of how to fit inflation into a bigger picture and attempt to realize this goal of using inflation to explain why everything we see around us is likely. And then I'm going to talk about my own new direction. It's very different from eternal inflation. I call the CITA equilibrium cosmology, and it's an attempt to realize the finite universe cycle. And then there's some interesting new results that I'm going to report at the end. They're observable effects. So, basics. The Friedmann equation, here we are. Friedmann equation, all the different forms of matter appearing with their densities. Each has their own scaling property with the scale factor. We can plot log plots of the densities. Here are the basic forms, radiation, matter, and I'm going to, for this talk, we talked about assumed dark energy is really a cosmological constant. You see a radiation dominated area, a matter dominated area, and a lambda dominated area. Let's zoom in, take a closer look. Here's sort of radiation matter transition. Now some motivations for inflation, the curvature feature of our problem. I like to be very careful about how we pose this thing. These things I'm not going to delve into it in this talk, but to set things up for conversations we might have afterwards. Whether the curvature problem is a feature or a problem, there's an interesting sort of it's important to think that through carefully, why you think it's a problem rather than a feature, but I'm just going to tell the standard spiel here. If there's a whole bunch of curvature in the early universe, it'll totally come to dominate the universe at the present time, which is the 0 point here. So it's huge, dramatically dominate. And even you can reduce it by orders of magnitude at early times, and it still dominates. And if you finally reduce it so much that it's actually consistent with data, then you worry about, do you understand why we had to tune it to such a tiny fraction of the total density at early time? So that's the issue with the curvature. And people don't talk too much about monopoles these days, but it's in some ways the most solid idea of the different ideas of motivated deflation. If you have a monopole formation in granulification, or really any component of the universe that scales as matter rather than radiation that somehow introduced at early times, that will also come to dominate, totally come to dominate. So, the way we approach that is to consider adding another peak component to the universe that causes inflation. We call it the inflaton. Its scaling is roughly constant with the scale factor. We can realize that behavior by having a nearly homogeneous scalar field with the standard gravitational coupled equation of motion with some cosmic damping coming in with the scale factor. And I added coupling to ordinary matter, which is important for reheating down the line. And really all potentials you might have for the scalar field have some region where you're basically overdamped by this cosmic damping. Sometimes it can occur at a local minimum, otherwise it might occur at large field as the potential grows large. But in general, you find some point in the potential that has this, the right behavior to give you the behavior you need for inflation. And then we can add a period of inflation at the early phase of the universe and look at something like this. This is actually integrating those equations right through reheating, so there's subtle details, but basically rho of the inflaton is constant at early times. We go over to matter and then radiation dominated era. And then we can introduce curvature of order with the same density as the inflaton at early times, because inflation sort of kicks out here. We can suppress the curvature value today. Likewise with a matter, a pressureless component, such as monopoles, we're safe from those as well. Just to illustrate a little bit more what integration I've done, here's a period during reheating where the solid purple is the density, the potential density in the inflaton, dash is kinetic energy. You see it's potential dominated, that's the inflationary state, it's potential dominated. Radiation is around because you have this coupling to radiation, totally sub-dominant on this logarithmic scale. Eventually, it stops the slow roll regime, the kinetic energy and potential energy become comparable, it enters an oscillatory phase, couples to radiation, and eventually the radiation dominates. Here's what the field is doing, and in this case it's just rolling in a simple quadratic potential. So this is just standard, it's an absolute standard law for inflation. You have lots of potentials, it's a simple one for that plot. Now, any questions so far? Very basic stuff so far. Now, in the rest of the talk, I'm pretty much going to be talking about length scales. And to start with, I want to talk about the Hubble length. And that's given basically by 1 over h. And I've actually mislabeled, I just noticed before I talk, most people don't call this rho code, it's rho critical. I just mislabeled the sum of these things because I encourage it as well. So let me convert the plots for the Hubble length are actually closely related. The density plots, first thing I do is plot the rho tote, just the sum of all these things that I've shown before. Remove all the indifferent ingredients, so we just look at rho tote. Change the scale a little bit, because the next thing I'm going to do is I'm going to look at this expression relating the Hubble length to rho, and I'm going to first of all take the inverse power, and that just flips it. So inverse power on a log plot just flips it to 0. Then I'm still need to take the square root of the Hubble length, so that changes the scale. And of course, once you've done a plot like that, you change the scale so it goes to the plot. So this is the Hubble length, but it's closely related to the density plots that I think are more widely familiar to people. This is a very standard plot if you work on inflation. And this is the inflationary period, radiation, matter, and in fact we can put these different components back on in Hubble length units, and we can see it's all there just like we had before. Okay, so that's the warm-up. Now we have a plot like this. It's a Hubble length across the entire history of the universe. And so I'm going to sort of show you all that by saying here, in a mark different important times. So this is the end of inflation, when the inflaton is no longer dominating, the end of reheating, when the inflaton is no longer slowly rolling, the end of reheating when the radiation dominated, weak scale, nuclear synthesis scale, radiation matter equality, and today we're not totally dominated by lambda, but we're close. So this is the whole history of the universe on one plot. Perturbations from inflation, lots of expertise here on that. But just the cartoon version is we have follow a co-moving scale that scales, that's length scaling proportion to the scale factor. When that length equals the Hubble length, we look where that's equal to the Hubble length here, and then it reconnects with the Hubble length plot over there, and the perturbation, the scalar perturbation here, is related to the evolution that's happening in the field during inflation here. And we can make these evaluations at different scales, and that's the standard thing. So, for example, going back to this detail, to get the amplitude of the perturbation right for physics, I have to tune this mass parameter to have certain values to get the right amplitude. And now, we have this, and this is the tool I was going on at the beginning, this is the tool that allows us to have beautiful data to analyze, and this is the tool that allows us to plot these curves on these beautiful results. And that's where these curves come from. So it's a wonderful thing. There's lots of wonderful new results, including ones that came out last month. And we had people here are responsible for a lot of this beautiful work. And so this is the great stuff we have, and maybe we should just be happy with that. We have incredible data, and we have ideas about how to plot curves and fit it. And in fact, I worked for some of my career long ago on a competing model that didn't have any of these features. And I actually think that's one of the wonderful things that's come out of the CMB data is the fact that long ago we totally discriminated against, between two totally different physical pictures, and inflation won in that competition. So it's a really great story, gives us a lot to be proud of, a lot of great physics to do. But now I want to go back to the question, does inflation make the standard Big Bang, meaning these sort of radiation matter-dominated eras, does it make it natural? And to ask that, we might move back and step back and say, well, how easy is it to get inflation? That's obviously where you want to start. How does inflation start? What kind of story do you have to tell about that? And maybe the way to get at that question is just ask what happened before inflation. So let's start with that. And to talk about that, I want to talk a little bit about quantum fluctuations. Quantum fluctuations during the slow roll period. So if we look at a region of the size of a Hubble length, there are constantly modes appearing and contributing, as the universe expands, contributing new contributions to the scalar field value in that region. So it's new, every Hubble time, there's a new incoherent contribution from a new mode contributing about h of field value. So you have this random fluctuation in the field set by h squared. And so we can compare the quantum, if we call this the quantum rate of change in the field, which is random, compare it with the classical rolling, this is the ratio we want to look at. And it's one and the same, really, within factors as the perturbation amplitude. And when the perturbation amplitude is as small as it needs to be to do realistic cosmology, that we're safely outside of the quantum-dominated regime, although actually this is intended to find slide a small number, but it's not nearly as classically dominated as most classical things we're used to looking at in the world around us. But it's still pretty classical. So if we go back to the question of what happened before inflation, well, we're rolling down like this, and the evolution is pretty much classical. It seems safe to assume that we roll from up here. That's a natural extrapolation. So let me now show you what that extrapolation looks like in this picture that you'll see a lot of my favorite picture. So the first thing I'm going to do, right. So we're going to, so this is standard Big Bang, this is inflation, and we're going to zoom out and just follow inflation as it goes on and on as the infotron starts further and further uphill. We're going to just zoom out and have a look at that. And so every slide, the previous slide, is marked in the blue box, so you can understand the zooming. One of the interesting things that happens, actually very, very generically in potentials, you might consider, is that as you go back with inflation, you go to higher values of this perturbation amplitude. So this is the universe we see. We tune the perturbation amplitude to be consistent with what we see, but then as we go back and imagine a whole more complete picture of the universe, we get to a zone where there are other behaviors. So we keep zooming out, the perturbation amplitude keeps going up, and higher, and eventually you reach a very interesting point where delta rho is the order unity, and that's when actually the quantum fluctuations start competing successfully with the classical rolling. And this leads to something called the self-reproduction regime, where there's a substantial probability fluctuating up the potential contrary to the classical rolling. And this is what leads to eternal inflation. The idea started with Linde, so I just realized I'm not filling, my slides are dropping off in its screen. It says Linde and many others. And especially actually bond, so the classic papers of bond cell effect for this whole quantum analysis of rolling is drawing attention to as well. The couple comments now. So I'm going to get into what the self-reproduction regime means in a minute, but just a couple comments before we go there. The observable universe has disappeared into a pixel or something on this plot. We've gone way up. Remember this, let's see if I've got I got to go back. But remember that black line is really all these times marked with all these lines, they've all shrunk down to one line. And it's really just the observable universe has totally disappeared. So we've done this massive extrapolation back in time and out into space to a grand scale, much larger than we actually observed. And that's just to get to the discussion of eternal inflation. We haven't even talked about eternal inflation. And so, for example, scales that eventually matter to us in the cosmos are several tens of thousands in the exponent, 10 to the minus several tens of thousands times the Planck length. So we're taking scales that at the start of this classical rolling period were this amazingly tiny fraction of 10 Planck length, and those are the scales that we observe on the largest scales of the universe today. So it's very, very dramatic extrapolation. By contrast, so this is a scale that's I've sort of arbitrarily chosen as 10 to the minus 4 of the Hubble length today, and that's just around the Planck length. So 10 to the minus 4 is a scale you might estimate as a lower end of the scale of inflation that we're actually observing inflationary fluctuations in the universe. So that we're getting down toward the Planck length, even here, and even past it if you look at these smaller scales. But we've really gone massive. It's a totally different story when we go back to this amazing extrapolation of this time. So that's sort of, so what I'm hoping I've done with this set of slides is helping you amazed just at the classical extrapolation we've done. And now we've reached a point where the quantum is dominant. And there's lots of, this is a very heuristic picture with quantum estimates of quantum fluctuations competing with classical. There's lots more sophisticated ways of detecting potentials to look at that much more systematically than I think well on it. I just want to make the point that you can crank through some numbers. The self-reproduction property is a very generic feature of any infracom potential. The key thing to look at is circled in red. It has to be greater than 1 for self-reproduction. And you can stare at this a little bit. Certainly if you have a potential, if you're doing inflation at the top of the local maximum, you can see that the V prime is going to be 0 and V is finite, so you're clearly going to have divergent behavior. Turns out something similar happens if you're inflating on some steep other kind of large field behavior. So it's a very generic feature. So this self-reproduction is not some fine-tuned, cooked-up thing for someone's special theory of inflation. It seems to be there everywhere. In fact, people who try to come up with non-self-reproducing infracom potentials really struggle, and there's no good example of that. So now I'm going to try to visually describe what happens in the self-reproduction regime. And that's notoriously hard. People have tried, many people here may have seen these beautiful pictures by Linde and Linde, but I think it's hard to know what they tell you. And there's other pictures that look like giant bonds that are also hard to interpret. So I've had another go, another try at trying to describe this. And so here we go. So I'm imagining there's a region of the universe that's in the self-reproduction regime. It's quantum dominated, lots of quantum fluctuations. And then some little coherent patch, the coherent scale of the Hubble length, slips down into the classically rolling regime. So some patch where the Hubble length starts rolling out of the quantum fluctuating regime and starts rolling. And I just, this is the Hubble length. This is about 5 times the Hubble length filling the screen. So I've just chosen that as my starting point. And then we move a little forward in time. We move along the timeline. Just another Hubble time. I've had to, because the whole thing is exponentially expanding, one Hubble time introduces a factor of e to the 2 in the overall scale. I'm tracking the exponential expansion. And the way you can see that is that the next region that rolls out into the classically rolling regime, again, is set by the Hubble length. I've rescaled everything up, but the Hubble length doesn't change. So then somewhere else where these are called pocket universes that start rolling classically, this looks smaller on the scale because it's a fixed physical, whereas the whole universe is expanding exponentially in this regime. Another Hubble time later, the new pocket is even smaller on the scale. I'm expanding. Everything's expanding together. And so now we have, okay, so we let that go, all this quantum expansion, exponential expansion. Then something interesting starts happening at around 500 Hubble times for this particular potential, where, so the eternal, the experts will notice maybe that I've done a little bit of finessing, but I've assumed the self-reproduction regime is just hovering right at the edge of the classical. It's actually occupying all kinds of territory up and down. But the self-reproduction regime is here. The inflation is slowly rolling down, and eventually its density is lower than up here, and its expansion rate is correspondingly lower. So eventually it fails to keep up with the eternal inflation regime. So that's happened after 500 Hubble times. It starts diminishing. I'm scaling 500 Hubble times. I've faithfully rescaled the whole picture by e to the 500. But now I'm starting to lose the size of the slowly rolling patch because it's not keeping up. It's slowly losing its expansion rate as it rolls down. And at this point, the new pocket universes are way suppressed because we've been expanding to 500 Hubble times. You can't even see it on the plot. So that's part of the picture. So we lose the classically rolling patch, but that's okay. We want to follow what's interesting. So let's rescale. So now I've suppressed the rescaling enough to follow. We're going to follow this patch. We're not going to try to keep up with the eternally inflating region. We're just going to follow this patch, follow it along the timeline, And then the next interesting thing that happens is this thing actually reheats. I showed you that earlier. Now we're going through the reheating. It's no longer exponentially expanding. It's no longer potential dominated. It reheats, and then even, so now I just fixed, looking at a fixed scale. I'm not changing the scaling of the box. I just watch this little patch disappear compared to the exponential expansion around. So compared to the exponential expansion, we lose track of this particular universe, and meanwhile the pocket universe, again, the new ones are just tiny on the scale because they're set by the Hubble length, which hasn't in the eternally fluctuating regime, which hasn't changed at all. So that's the picture. So that's my attempt. I've insulted everyone else who's trying to make pictures of inflation and of eternal inflation. Now you can judge whether my picture has worked any better. Well, you can tell me afterwards what you think, but that was my attempt. Now I'm going to list some features of eternal inflation. So most of the universe is always inflated. That's the picture. That hashed region totally dominates. It leads to an infinite universe, infinitely many pocket universes, and the self-reproduction phase, that is the quantum fluctuating hashed phase that I showed in the previous slides, lasts forever. Now you've got to be careful about that. It lasts forever globally. If you take a local spot, it will always diffuse down into the classical regime, but because you're constantly producing exponentially more volume in this quantum regime, that lasts forever, never stops. Inflation, so it seems like you might have a good theory of initial conditions, because if you could just start a little bit of inflation in this eternally self-reproducing regime, it seems like we just take over the universe. So who cares? Who cares how it started? Who cares how probable it is to start that? It just totally takes over and gives you this infinity. So it seems like a pretty good theory of initial conditions. Now comes the tough part. So because you have infinitely, it seems to last forever, you have infinitely many pocket universes, these little classical things that roll down. And so you need to regulate those infinities to make predictions. So if I have different pocket universes with different properties, and I want to ask which is more probable than the other, well, there's infinitely many of those types, so I have to regulate that infinity in some way to come up with some concrete numbers. And typically that's done by using some kind of finite time cutoff, effectively a finite time cutoff, as a regulator, and then letting that cutoff go to infinity. That's the standard. There's a bunch of different so-called measures used, but they all involve some kind of making it finite and then letting that cutoff go to infinity. Now, something you can even understand at this cartoon level is that for a specific time cutoff, the most recently produced pocket universes are exponentially big. So I can take, if you remember my cartoon slides of eternal inflation, the very first pocket universe that started rolling down, that's one universe. But you're producing pocket universes at a constant rate per unit volume forever and ever and ever. So if you put in a time cutoff, the most recent pocket universes are the ones that waited as long as the most numerous pocket universes are the ones that waited as long as possible to gain the benefit of exponential expansion of the volume, and then produce themselves at a constant rate per unit volume. And so the longer you wait before forming the universe, the more likely you are. So people find that in this specific time cutoff, you can call it the young universe problem. So you do that, you put in your cutoff, most of the universes have just been formed, and you take the cutoff to infinity, and none of that changes. Most of the universes are young. It can be called the young universe problem. Other people call it the end of time problem. It's really the same point, sort of couched in a slightly different form. I'm not going to try to separate the two for the talk, but we can talk about that afterwards. It's basically the same. I'm making the central point right here. And then, more generally, this is known as the measure problem. The people say that there's something called a scale factor cutoff measure that looks better, but that's, and it sounds nice, because what could be wrong with using the scale factor? That's what we always talk about in cosmology. But what you're doing is you're putting a cutoff of fixed scale factor, which means the parts that have been exponentially expanding at scale factor, the huge sizes, you discount that. You sort of go back in time to put the cutoff early for those parts, and then anyway, it looks like when you think about it, it looks very distorted from a certain point of view. So it's an unresolved puzzle how you actually make physical predictions from this picture. And in fact, it's gone off the screen, but the state of the art here is that instead of making predictions these days, the experts are using the data to infer what the correct measure is, what the correct technology of the cutoff and the regulator is. And so instead of predicting beautiful curves from the data, they're actually using the data to infer how inflation should work. So it's totally turned the sort of idea of inflation on its head when you try to investigate these problems.
How do you infer a measure from an example of one?
Well, that's a classic. I mean, if you think you're predicting probabilities, and your probability is exponentially suppressed for our universe, then you reject the theory. If it's ridiculously low probability, you reject the theory. We're used to that. People have existential angst about that, what if we're an outlier, blah, 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 but that's what we do. That's how we use probability. So it's no different. It's no different. And there's lots of data. So it's not one data point. There's lots of data. So now we're getting into the difficulties of eternal inflation. So that's one statement. And also it's very interesting. So this idea that it takes over the universe and is a good theory of initial conditions is people believe, and I've had some really interesting conversations with Alan Booth, especially over the last year, on this subject. Alan certainly believes that, and he's probably right. And sometimes I want to, it's sort of a slightly open question in my mind, but the going idea, and anyone who wants to talk about this, just a simple point to really illustrate what this is about, is that unless you really let the eternal inflation go for infinity, never ending, ever, it turns out it's not such a good theory of initial conditions. That you can worry about that to get if it's finite, then there's going to be some basin of attraction in initial conditions before inflation to get you to inflation, and others that don't. And it's not so clear which wins unless you assume that inflation goes forever. So the going thinking is that you really have to assume this thing runs forever, not a very long time. That bothers me because in my whole career as physics, I remember as a student puzzling about the meaning of infinity in physics and concluding that for physicists, infinity shouldn't mean anything different than a very large number, very large or finite number. And that any difference between the two was philosophy, not physics. And that served me really well for a long time. This is the first time it's really been stretched. That I've encountered colleagues who think that in physics, where they really need the infinity as opposed to just a very large number. And so I'm wary of that. It's one of the additional things that makes me uncomfortable with eternal inflation. I'm not talking about the landscape in this talk, but the landscape just makes it worse because there's lots of inflating regions, and so it's just the whole thing. So if you're confused about what eternal inflation means once, you're even more confused about what's happening in the landscape where there's inflation going all over the place. Not necessarily slow roll, but similar issues are in place. So makes it even more challenging to think about the landscape. I'm not going to talk about it all, but if you really have an infinite universe, there's multiple copies of you. And Don Page has pointed out there's really, you can't really use the Born rule when you thought you would, if that's the wave function is like. And that's a really fun topic for other conversations. Oh, so that's my, I forgot to lead into the slide, but when you, so the problem, so eternal inflation has some nice features, but when you try to actually calculate physics, this is what happens. And the problem has been detected and your calculation has been shut down or been damaged. You've encountered a relative probability overflow. This is the first time we've seen the stop error screen restart your calculation. The screen appears again, follow these steps. Check to make sure all extrapolations are justified and equations are valid. That's where I'm going to go with this. If you're new to this calculation, consult your theory manufacturer for any measure updates. So the experts who are into this eternal inflation business are always trying to think of new measures, new rules for measures that might fix the problem. So check with your theory manufacturer for any measure updates. If the problems continue, disable or remove features of the theory that cause the overflow errors. Fair enough. Disable. So I've copied the blue screen crash right here, so this is BIOS. Disable BS options such as self-reproduction or infinite time. If you need to use safe mode to remove or disable components, restart your computation and utilize it. Here we go, holographic. So now this is leading into my own thinking about the subject. But then I'm reminding you, by the way,
that you can't get away with introducing an S-landing and saying what it is.
Yeah, well, yeah, that's nice.
Okay.
So, or remember now, you might just be happy you have some equations to solve to fit this beautiful data. So hold on, and let's see where we go. Consider equilibrium cosmology. So it takes ideas from holography, from a cosmological constant to construct a finite cosmology. Also builds on the initial motivation that I talked about at the beginning of an equilibrium system not having a puzzle of initial conditions. I like to, so what I'm going to do, maybe I'll add the second point here. So whatever point it is. Anyway, I like to make the point that no one's theory of inflation, eternal or my theory, is based on things we're sure about in fundamental physics. Each one is a speculation about whether you're extrapolating classical equations to infinitely long time, or whether you're doing the kind of assumptions I make to consider equilibrium cosmology. No one can count on the physics they're using to describe the cosmology to be actually correct. And so you could say, well, maybe this is the wrong time to be asking all these deep questions about cosmology. Maybe we need to wait until someone's worked out the right theory of quantum gravity, and then we can see how cosmology moves. And there's some days when I feel that way. So some days I have this sort of darker view of doing all this work. But other times, I see this as a really fantastic opportunity where we have a hint. There's something really right about inflation. All these beautiful data sets are totally confirming the basic idea that there was a period of positive inflation. So why not ask ourselves, what does it take, what do you need to do to make a theory of inflation that actually works, to complete the picture, to complete the fundamental physics in a way that lets inflation actually work? And the hope, our greatest hope, I think, could be to do the equivalent of finding the Bohr atom for cosmology. The Bohr atom is not real quantum physics, but it helped people find their way. By trying to ask how an atom needed to really work, it helped people find their way to a good theory of atoms. So if we're lucky, and I don't claim I know we will be, but that's the optimistic view, that we can try to make inflation work, ask what kind of assumptions do we need to put in, what kind of ideas about fundamental physics do we need to put into the picture to make it actually work. Maybe we'll get some guidance about how the fundamental physics really works. So that's the optimistic view. And it's also just a counterpoint. It's definitely finite. It's a totally different way of thinking than eternal inflation. So it's an interesting exercise. And I just want to warn you that I'm unabashedly exploring uncertainties about fundamental physics. Some places I'm assuming continuum field theory is good, but I have a truly finite system that doesn't really can't really be true. Continuum field theory is an infinite set of degrees of freedom, so something has to break down. And I unabashedly choose where that breaks down and how it breaks down to construct realistic cosmology. So I'm not pretending I have this all figured out at some level. I'm trying to put ideas together to make the cosmology work. There's papers, so if you want to see papers, there's papers. So to describe what I'm doing, of course I go back to my favorite picture, clear off some of the declaration, and zoom in on late times. So this is now late times. This is the period of cosmological constant domination. I need to assume a true lambda for what I do. And now let's look at some asymptotic behaviors called de Sitter space. And now here, I've marked, this is essentially time, this is an event, an observation. And this is the past horizon of that event. And what that means is, if I observe a photon at this time, and I'm co-moving, so I'm sitting in the universe, not moving relative expansion, and I see a photon, how far away was that photon from me at all these times in the past? And this is the answer to that question. It's called the past horizon. It's kind of interesting that even though the photon's traveling toward me as the universe expands, the distance is actually increasing, because if you're at a distance greater than the Hubble length, you're expanding faster. The distance is increasing faster than the speed of light, which is all the photon's got going for it, is the speed of light. And then only when the Hubble length catches up with the photon does actually start coming toward me. So this is the past horizon. And then here is another observation event. You'll see that the past horizon looks pretty much the same at earlier times. And that's because the de Sitter space has a horizon, has an event horizon, much like that of a black hole. So any observer, no matter how deep in the de Sitter space, will only observe physical scale, only observe physics in this finite region, marked out by the past horizon. So this is a very important feature of the de Sitter space. And by the way, if you're wondering, hey, I learned about horizons in Coleman Turner or somewhere, it's a totally different horizon. It's not a totally different place. I don't think it's a different place. So that's what that slide's about. The implications of the de Sitter horizon. It's been shown by Gibbons and Hawking, the first paper really on the subject, that well, a horizon, with horizons, people are used to associating entropy, just like the black hole entropy. The horizon area gives you an entropy, and Gibbons and Hawking showed this is actually maximum entropy, a space with a lambda in half. So you take the de Sitter space, chuck in the black hole, you think you're adding entropy because the black hole has entropy, but actually the de Sitter horizon shrinks when you put in the black hole, and that turns out to be the dominant effect. So you throw in a black hole that reduces the entropy, black hole decays, and the entropy goes up to the de Sitter value. So that's the maximum value. So by the way, that sounds pretty good. If you're going to talk about an equilibrium state, having maximum entropy is a pretty good attribute to go for. It has a temperature, a given target temperature. And so we could ask the question, should the de Sitter space, just drawn in this cartoon picture with illustrating the horizon, can that be the ultimate equilibrium of the universe? It certainly is a state that we, if you think a nice heuristic definition of equilibrium is the state you get to when you wait a long time. That's certainly true about de Sitter space. It has an entropy, it has a temperature, so it's pretty good. So I've listed these properties of the de Sitter horizon. I've emphasized these 2 points already, maximum entropy, given some temperature. Only a finite volume is ever observed, and so you may well ask the question, if you never observe anything more than a finite volume, is it just metaphysics? Do you even think that there is a universe out there beyond that finite volume? That's where I really start thinking about a finite space. Furthermore, if the entropy is finite, there's a maximum entropy, then why should I think of anything but a finite Hilbert space? If entropy is the logarithm of the number of states, and the entropy is bounded by a finite value, what does it mean to even think of a Hilbert space as larger than either the S lambda dimension? more than EU as non-verifiable states. It's people have made the argument, Banks, Fischler, and others, sometimes Susskind have argued that you should really think about this as the meaning of this S-Lambda is that it gives you the dimension of Hilbert space, the finite dimension of Hilbert space of your physical fundamental theory. So these are the ingredients I'm going to use to build the de Sitter equilibrium cosmology, and especially these last ones I'm going to exploit the hills. Okay, equilibrium cosmology. So I have 5 minutes, right? So most physicists, when they think about equilibrium, revert to the box of gas. We can think about a box of gas as a equilibrium state, but we know it can have rare fluctuations, where, for example, all the gas goes in the corner. And those rare fluctuations, so even though in the sort of standard equilibrium state, there's no arrow of time, because the entropy is just fixed at the maximum value, there is an arrow of time here, and it points in the direction of increasing entropy. So it's actually a double-headed arrow of time, pointing away from the minimum entropy state. So in an equilibrium situation, you can wait for rare fluctuations that give you a transient arrow of time that occurs in this package of double-headed arrows. So that's, now, this has been considered for more than 100 years. It's known to have the Boltzmann ring problem, which suggests that if your universe is really like this, then the most likely fluctuation is the cheapest one you can get to describe what you see. So maybe if we know this room exists, and the most likely fluctuation is just this room fluctuating out of chaos, and then dissipating back in, if you work to sort of push back to the smallest possible scale, maybe it's just your brain or the neurons or whatever fluctuating out, and you believe all this stuff is around you, but you're wrong. So that's considered a technical problem. No one really knows what it means for what the minimum degrees of freedom of your brain are, but it's a technical problem. If the most likely universe is a small one rather than this giant one we see, that's a technical problem in cosmology. I'll come back to that. So the concept is this equilibrium state. The realization of my picture is the de Sitter space equilibrium. The fluctuation is a rare fluctuation, and in the de Sitter space, there's a process called the Guth-Farke process that dominates. If you have an inflaton in your spectrum, that inflaton has a chance of fluctuating like a hill and making and seeding an entire inflated universe. And there's a whole technical process for calculating that. And one of the interesting things is that if you have gut scale inflation, the minimum seed mass you need to fluctuate is about 1 gram, and that's, I don't know how much is just the neurons of your brain weigh. I don't know, but it's kind of interesting that if whatever you're competing against weighs 1 gram or more, then it's cheaper to get a whole universe out of inflation than whatever little fluctuation you're competing against. So that's, I think, an interesting insight about the Boltzmann ring problem. It gives you hope that this kind of picture will avoid the Boltzmann ring problem because of the interesting properties of inflation. You can take a small fluctuation and create a whole universe. And there's new work on the Guth-Farke process about to be published. I'm not going to take the time now to talk about it. So the general picture is you have equilibrium, you see the fluctuation, it buds off a baby universe, it goes through the standard Big Bang. Because it's finite, it eventually has to recohere. You don't have infinite degrees of freedom to keep producing baby universes, just spewing them out infinitely. Once you approach de Sitter equilibrium, it's the same de Sitter equilibrium you have to start with. And this is what makes it different from other ideas that sort of have at least broadly similar form, but not explicitly defined like this. So the implications of a finite Hilbert space, you have recurrences in this picture. There's not an infinite variety of states you can go through at average finite time. You can do them all. So that's what causes it to repeat here at the end. We have equilibrium, and I've just warning you, I've assumed the breakdown of continuum field theory. So I've got just a minute or two left, and I want to make my point about observational predictions. So in this picture, you have to impose the finite entropy. You cannot have continuum field theory just describing the whole universe. That's what stops you from having eternal inflation. And let's see how that stops you. Because this is how much inflation you need. This is a past horizon coming down. This is how much inflation you need to just fill the one considered horizon. If you have more inflation than that, first of all, you'll never see this stuff. And second of all, you'll produce more than the maximum entropy. So in this picture, we claim, and really it's conjecture, because that's what we're doing, is putting together ideas with this particular goal in mind, is that we claim the finiteness, the lack of a true continuum field theory will kick in to prevent you from having more inflation than just enough to fill one considered volume. So this shaded region is just unphysical in this picture. It's a wrong extrapolation of continuum field theory. That's the claim. The universe is really finite. We're exploiting that finiteness to see a finite picture of inflation. And then I've already talked about the Guattari process. I just want to make the point that Guattari tends to prefer being as high up the potential as possible. And so that means inflation models tend to saturate this considered equilibrium bound. So these are a whole family of inflation models. Low-scale inflation, high-scale inflation, long reheating, short reheating. There's actually something like 40 different inflation models. There's actually real inflaton potentials and couplings to radiation and all that fully integrated and put on here, but they've all been forced to start at past horizon. So now the prediction, the last punchline of the talk. In the considered equilibrium, the Guattari process starts with a bubble. The bubble has curvature. Let's look at, so here's curvature. It goes as a to the minus 2 in the picture, and that means when we put it on, the curvature length also scales as a. So outside the Hubble length, the past horizon scales as a, and so does the curvature. This gives a beautiful unified picture that regardless of what the different inflation models are doing, slow reheating, fast reheating, large scale or small scale, the unifying idea for considered equilibrium is they all start on this blue dotted curve. And they all start with a bubble curvature set in relation to the Hubble length that's given by this black line. So the height, the separation between the Hubble length at the start of inflation and the curvature is set by the bubble curvature from considered equilibrium. And if we set that to be the same for each inflation model, we get, what it turns out is we get the same prediction of curvature at the end. So this is where I'm going to rush to the punchline and we can talk a little bit about the details. I have a paper where we discuss the analysis of how we get there. But I think I'll just, we have a formula that looks simple after you've seen it once. But the prediction is here. That the prediction of this theory is that if we know the bubble, so for a given value of the bubble curvature, the only thing our predicted curvature depends on is the ratio of the matter density today to the lambda value of lambda. And so these things we're going to measure really well. This is already fairly well measured. It will be much better measured in the future. And so all we need to do is understand the bubble curvature, which looks like it can't be a lot smaller than 0.1. So we have a prediction of an observable level of curvature that's actually just consistent with what we observe today. So my punchline is that here's a theory. It's highly speculative. Who knows what parts might be right or wrong. But the exciting thing to me is it actually makes a prediction of something we can observe. So if we go out, if the data gets better, and we actually observe some curvature, I would say that's a really exciting reason to take this theory very seriously. If curvature is not observed down to orders of magnitude below the current bounds, That's a problem with this theory. You get tangled up in exactly what the bubble curvature can be or not be, but I think actually that's easy to resolve, and I don't think the theory can stick around if the curvature is zero in the next 10 years of data. So to me, I love thinking about these big ideas. It's not always, doesn't always feel good because you don't know how well you're going to test them. It's really exciting to come through with a really simple prediction. This just doesn't depend on the inflaton potential, the reheating, all kinds of details of cosmology are just completely disappear off of this prediction. It's a really simple prediction and something you can really look at. So I think we're done. Conclusions, search for the big picture of the universe is exciting. It is difficult, but it's generating exciting ideas. On the other hand, we know we can do science with the universe, so I really think we should be trying this stuff. We shouldn't just give up and say, well, we got something calculated, that's enough. It appears that there's something right about cosmic inflation. The state of equilibrium cosmology offers an alternative to the incredibly extravagant and problematic infinities of eternal inflation. And as I've been saying, I think it's really exciting to have a prediction to help us, to help guide us, and help use data to guide us in this direction. Thank you.
I ask you four basic questions regarding the entropy of the sitting universe. So I imagine there's no cosmological constant. Then I am instructed to think of the universe as being unbounded. The horizon expands. It encompasses more and more entropy. But I add in, transition to exponential expansion, and that's like a cutoff.
Right.
And so the claim is that the entropy that you accumulate within your horizon, just through the particles and other stuff, black holes, is bounded above the entropy of the sort of horizon. Okay.
And it's dominated by the horizon entropy rather than jump.
But when you have the transition and then omega lambda is equal to omega radiation.
So going through here.
Suppose you have the radiation dominated universe and no nominal matter. Then the two entities would be, I assume, would be comparable to the
No, it's subdominant. So the entropy is really a horizon entropy, and it's not realized in the volume. That's a subdominant contribution. Yeah. So I could throw. I could throw. Oh, that's exciting. We're synchronizing my calendar. We could throw. So here's an exercise. Take a de Sitter space and throw in radiation of equal density to rho lambda. That will reduce the that will have a subdominant reduction in entropy. It will reduce the entropy first of all, and there will be a subdominant. So the entropy will be S lambda with a small correction. We could go through the equation.
Well, I can see the different ratios of Planck length, Planck mass to and it's what's the coming up. The last question is just how does this all connect up with, say, the many worlds interpretation of quantum mechanics? I imagine this foliation of different outcomes of the initial conditions.
So that's actually really fun. So let me.
And then does this mean
so let me.
Can I just ask a question? If you go to very large scales, you just go to the pattern of microwave fragment anisotropes that you see in the sky, that there's a different number of things that Magnolta is doing depending on which unit he's doing, but he's still seeing the same, he's still doing the same measurement.
So here's the key. So the branching of many worlds is absolutely deeply connected to the arrow of time. And once you saturate the entropy, you're just as well branching in as branching out. And so, in other words, you can't say this is my classical world, I made this quantum measurement, because you don't know what quantum fluctuations are going to come in from other paths because you're in equilibrium. And so it's only when you have a good arrow of time, a good quantum path. So the quantum arrow of time, the sort of collapse of the wave function, all that good stuff. And the many worlds picture is just harnessing the thermodynamic arrow of time to make your apparatus work. And once you run out of arrow of time, you run out of, I mean, you still branch, but you branch in just as much as you branch out. There's no outer foliation.
In the sort of vacuum, there is no arrow of time.
Yes. So then there's no sort of, yeah, the branching idea of many worlds has changed dramatically to an equilibrium version. So you use that up at the end, when you hit the Sitter equilibrium. You don't get it again until you wait around for random fluctuation to bring the entropy down. And
Should I think that all this branching process is being scaled 10%? You know, I mean, if I go.
But there's only one thing flexible conditions. That there's only a
well, maybe
I don't know about that, but I don't want to.
we can maybe over coffee we could have
Yeah, one more question.
So the difficulty I have is that we don't really understand the Sitter space very well. And the issue of equilibriums is one of the shrinking limits of the Sitter space. The question is, if you have this pocket coming out of the Sitter equilibrium, and the Sitter will have a transsymmetric situation to it, but then of course the pocket locally will have an arrow of time. And then this pocket gradually will go back to the receiver.
Yes.
What happens to the arrow of time? Does it go back
It
to the
goes away.
transsymmetric?
So first of all, the fact we don't understand the Sitter space really well, I'm exploiting to my benefit, and I don't mean that. I mean, I'm glad I'm doing it, but it doesn't mean I agree we don't understand it well. So I'm exploiting that. And I know actually you've done lots of beautiful work that's similar in many ways, but you've looked at a more infinite picture. If I recall correctly. The question of how it, yeah, so you have this tunneling event that produces a low entropy state, and then you return to equilibrium. So that's sort of what I tried to illustrate here. So you have the Sitter equilibrium that has a random fluctuation. There's a tunneling process that builds off the big universe. Some degrees of freedom are tied up in that big universe for a while, but once you equilibrate, you only have either the S lambda degrees of freedom, and so the equilibrium between these two is, you can't differentiate between the two, and it becomes the same. If you think, suppose for example you have a wave function for a box of gas, and it's coherent superposition of a piece of stuff in the corner and a piece that's just nicely in equilibrium. And you follow that over time. And for a while, there's a really good reason to think of it as that superposition, because there are two different things going on, and it makes sense to track them. But once the thing in the corner equilibrates, there's really no sense in thinking of it as two pieces. You might as well just combine them together. Some state and called another equilibrium state that's different only in subtle ways that you know.
Would I locally see this as a quantum?
Sorry.
Would I locally observe this as my universe becoming quantum again? Or this process of equilibration?
Is this? Well, I'd say it's quantum. It's quantum again in the sense of the discussion of Chris. If you don't have narrow time, you don't have quantum measurement as we know it. So you're stuck. Quantum fluctuations dominate in this sense. You don't know if something happens. You don't know if it. You can't extrapolate classically back. You don't know if it's just some random fluctuation. And in fact, an important part. So this idea of a finite horizon has been explored by other people before me. Susskind is a big advocate, and Banks and Fischler have thought a lot about it. And they really like the idea that in a Sitter space or in a black hole, there's multiple. You don't know if stuff that seems to be coming off the horizon is really some concrete part of your classical solution, or just a thermal fluctuation off the horizon. And that's the sense in which it's quantum, because those thermal fluctuations are quantum effects in this picture. So you really lost classical physics. I don't know, did that help?
Yeah, absolutely. Because I was thinking of the equilibriums you described as low and very necessarily for humans land. That tells us that once we go beyond that land, we are really looking at the concept of the observers and the classical.
Okay, I think we're gonna have to cut it off there. In some universes, there are